Perfect. Recording has started. So welcome to our lecture on machine learning. You're all done with the quiz, the bonus point quiz. For every correct answer, you get a bonus point. You can have another 1-2 minutes, no problem. We have time. This is also the benefit of the bonus point quiz. So I have time to clean the blackboards before we start. Maybe we are fine with 3 blackboards. I think so. 3 should be fine. Yeah. Good point. Projector number 2. You just need it for the link to the quiz. I don't have many slides today. Maybe some words to the exercise on Friday. In the assignment 2, you will be asked to implement a basic class with some members, some methods. And that's pretty easy. You can simply let ChatGPT do it for you. But in the end, I also ask you to create an entity relationship diagram which uses this class, and you have to invent some new additional classes and describe the relationships between them. And then you have to be creative. Then it becomes more difficult for ChatGPT without concrete instructions. Well, so let's have a look at your answers. 37, 36 users and 33 users. Some of you are still voting. Let's wait one more 30 seconds. It's fine. So you might have seen the humanoid in the first lecture. We have just ordered it 2 days ago. We hope that we will get this complex system very soon. So in the next 12 weeks, 8 to 12 weeks. And ideally on our big opening event on the 13th of June, you're all invited to come to our big new building. We would like to demonstrate all our systems, including this new one. There will be a nice buffet here, public speeches by politicians and our president and our vice presidents. And we will have interesting live demonstrations of our research in our lab. So that all will take place on Friday, the 13th of June. We start here at 11, I think. And at 12:30, we start with the demos. But these demos will be guided tours. So you need a ticket or something, or you need to group up somewhere here, and then you will be guided to our building. All the other chairs in this building will also show what they are doing in their research, and also the chair of automation. So this might be also interesting if you're looking for a master thesis in the future in one of the fields, logistics, information theory, machine learning, robotics, or automation. Maybe that's an interesting event. But let's start. Let me make that bigger. You can all read it. So, which of the following statements on data pre-processing strategies are correct? The first one is wrong, for sure, because nobody ticked it. Huh? Then the second one, data normalization and standardization are useful to transfer experts' knowledge, for example, on hyperparameter choices or pre-trained models to new tasks. So this is essential. This is correct. And that's really one of the major reasons why you want to normalize your data. So ideally, you want to apply the same settings for any problem using the same model. And here normalization or standardization, they help. Standardization describes zero mean unit variance transformation. That's correct. K-fold cross-validation is a strategy to generate trained test splits using K-folds. That's also correct. And the last one is wrong. Well done. Number 5. On parametric and non-parametric models. Well, this is an important one. Parametric models need to store all data points. That's wrong. Non-parametric models require to assume a model. That's also wrong. Parametric models are memory intensive. That's also wrong. And the last two must be correct. Non-parametric models learn abstractions. Yes. Yes and no. Actually, this is, one could discuss that. There's a tricky answer. Because what are abstractions? Define it. You learn something from data that could be reapplied to a different task. That's an abstraction somehow. So a more general form of information that could transfer to different questions, problems, predictions. So I would say this answer is correct. I count it as correct, but it's a bit tricky because normally we say abstractions are given by the model itself. We assume a model and the model itself implements these abstractions. But it might be that your non-parametric model is also learning abstractions, your data-driven approach. Parametric models generate predictions based on parameterized models. That sounds good. All right. And question 4. This is about general statements of machine learning concept. The first answer is obviously wrong. So there is no single model that would solve any problem on this planet. And the second answer is correct. The no free lunch theorem correctly states that there is not a single model or algorithm that works optimally well in all different scenarios, on all tasks, all problems. Let me read that about overfitting. Here you have to be always careful how you define these questions here and their answers. So this is wrong because with an increasing number of training samples, the training error decreases, which is correctly stated here in the last answer. So last answer is correct. The second and the last answers are correct. Any questions to the quiz? Please fill out your points. Yeah. Second question, second last answer. This one? Whatever you choose is correct. So this is really problematic. I can't remember why I added this answer to the multiple choice question. Maybe to discuss it because it's really something one would need to discuss. And with the knowledge given in that question, it's not enough. All right. So learning goals are always important. Actually, learning goals help you to understand what will I ask in the final exam. Because I wanted to be able to solve these things, to know these things, to describe these things, to understand these things. These are my learning goals here. And today, I want you to be able to read and understand and actually use the mathematical notation that we use in machine learning. So I will start with that. I want you to be able to apply basic matrix calculus operations to solve problems. And I will show you something and you will be able to solve that afterwards. Then I will discuss distance measures, Euclidean norm, everybody knows it, but there will also be a bit more general because we need it always, these norms. And in the end, I show you an example where we use matrix calculus on an example that you all know, where you have to fit the line to some data points, and it's nice if you have only 4 points or only 2 points, but it becomes more complicated if you have 1 million points. And with the tools that I will demonstrate and discuss with you today, you will be able to solve all kinds of problems, regardless of the number of points. So this is the outlook then. I will start with some basic notation that's a bit dry. Then I will present these norms. And in the end, we discuss a linear regression example. And here in the slides, you find some basic rules. I won't go through that. So the slides are not really representative for what I'm doing here on the blackboard. And that's now also the drawback of the video recordings. For me, it's really hard now if I turn off the projection. How should I record properly the blackboard with WebEx? So far, I have no solution for that. So in the past, I always turned on my camera here. Then you would see at least this blackboard here. So I can always use this one, this side for today. Maybe that's a proper way to record what I'm doing. I like this color. So, number one, the notation. Well, in machine learning, we love to use vectors and matrices, and we love to use standardized conventions that simplify all the descriptions. And the most important one is the definition of a vector. Typically in a textbook or in a research paper, you will find these vectors to be lowercase and bold letters. Here on the blackboard, drawing bold letters is a bit difficult, so I'm using underscores, underlines. And then you have individual elements, xn, and whenever it's not defined, you have to assume that this is a column vector. And how do I actually additionally describe that? Well, I say this vector is of real elements, real numbers, and it has the dimension n times 1. So then it's fully defined. Now I might have a different vector. Let's call this y. Let's do it that way. y1, y2 till yn. Same number of elements, so this is also an n-dimensional column vector. And now I can solve something called a product. I will ask in a second what for product. What is the result of this y transpose times x? Is it possible to do that? To apply this product here? And how is it called? Well, we have vectors. Yeah, and it's a special form. What is the result of this product? Is it a vector? Is it something else? Really? 3 type 3. Now let's have a look. What I typically do, and I also recommend it, highly recommend it in the exam, whenever you derive something, leave enough space after your equation such that you can define the dimensions. You have Rn times 1 times Rn times 1, but this thing is taken to the, you apply the transpose operator to the first vector. So in the end, you have R of 1 times n times R of n times 1. And we call this number a scalar. And it has the dimension R1 or R1 times 1. So the result is a scalar, and therefore we call this a scalar product. So you already see that there is a lot of information in this notation. And it's very compact. Now, of course, if we use matrices, then I use capital letters like this one, X, X11, X12, X1M, and it goes down to XNM. Now, what is the dimension of this one? Of this matrix? How many rows do I have and how many columns? I have n rows and m columns. Now, is it possible to multiply my y vector with this matrix? And how? So there are two options now. What options do I have? I want to multiply this matrix X and Y, the vector. So option A would be yes, X transpose times Y. That would work because in this case, I would have the dimension Rm times n times Rn times 1. And the resulting dimension would be, so for those who never used such notations, whenever you solve a product, the inner dimensions, so the dimensions of two neighboring elements, whatever, vector, matrix, have to be equal. So they need to match. Otherwise, you can't do that. Another thing is, if you solve that product, well, the resulting dimension will have the dimension of the outer elements, m times 1. There is a course called matrix algebra at this university, but it's first semester or second semester bachelor course, and you might not have had it. So therefore, I'm a bit slower today, try to explain everything, but ask me. Yeah, no wrong questions, just wrong answers or incomplete answers. So what is the option B? We can transpose the vector and multiply it by x. It's also possible. So why is this important? What do you think? Why is it important to think about the dimensions and how I need to multiply these things? We come to that. I will show an example at the end of this lecture, and then we will make design choices. And based on our design choices, we have either option A or option B. And we decide how our model is parameterized, if it's column vector or column vector transposed, which is a row vector. The thing is, whenever you read some paper, you need to be clear about the notation and verify that actually everything is correct. And sometimes this notation is preferred for some linear model, sometimes this one, where X could be your data samples and Y might be your model parameters in linear regression. Done. Ah, yeah, matrix product. Okay. Just for completeness, if you have two matrices, A times B, well, you all should know how to solve this product, but just for completeness, let me give you one example. Because we are not in a rush today. So we have a 3 times 3 matrix. We multiply it by, what options do we have here? Exactly. So 3 rows, whatever, number of columns. B1, B2, B3, B1, 2, B1, 1, B1, 3, B1, 4, whatever. That could continue. And so on. And if I want to compute now this product for some element, for instance, C1, 2, well, then C1, 2 is given by what? Tell me. Exactly. And what's the name of this product? We are again computing here a scalar product. So this is a scalar, the result. Hmm. Good, well done. Well, there's a different product. I also want to mention it here. If you see a notation like that in a textbook, what does that mean? This is the Hadamard product normally, but to be precise, you have to define the symbol because there are different notations and some scientists use different symbols to denote the Hadamard product. And here, the difference is that this is an element-wise product. So here, C12 would be what? Exactly. So here you only take two elements. So it's B12 times A12 or vice versa. Really element by element. And here the dimensions need to match. Can you read everything also from the back? Yeah, okay, perfect. I will try to use only this side such that we have at least some recording. Will take a little bit longer because I can't use these three blackboards, but it's okay. Now I want to talk about distance measures. And I will start with something that you all know from high school. And I will start with a sketch. So, number 2, norms, losses, or distance. Measures. Okay, I start with a drawing. A, B, and C. Let's see if I get that right here. Well, now I have to be creative here. What is that? You're a technical high school teacher. Yeah. Yeah. What kind of triangle? So you all know that from the rule of Pythagoras, you know that c squared is equal to a squared plus b squared. So this area here defines an equation. Now from that, I can compute the length of the line segment C by taking the square root of a squared plus b squared. Now, ancient Greek scientists named Pythagoras and Euclid worked on the unity of line segments. They defined such rules based on equal line elements or line segments. Now, why is that interesting? That is interesting because we can compute the distance between points. P1 and P2. What is the distance between P1 and P2? Tell me, what do I need to write down? So, yeah, okay. You are right. I have to define the vectors here. And I was lazy, I forgot my underlines here. So we have P21, P22, P11, P12. Now C is given by what? P21, yes. All right. Perfect. Now, can you define a more general form using vectors instead of using scalars here? So you used P21, P12, and so on. So that's a bit cumbersome. Are there options to use vectors? So in the end, let me think. What do I need to write down now if I want to use vectors? Let's start by defining dimensions. That always helps. So I know that C is given by the square root of something which has to be of which dimension? Whatever is inside the square root has to be of which dimension? A scalar. Now I know that my 2 points are 2-dimensional in this example. They could be 100-dimensional. We don't care when we are done. I know that I have to compute the difference between these 2 points. So there must be something where we have P2 minus P1. Both are vectors. So this is of the dimension R2 times 1. Now what can I do to make that a scalar? And there's also something missing. Something important is missing. What would happen if you do that? So you multiply the transpose of the difference times the difference of the 2 vectors. Would that be equivalent? Give it a try. You can solve it yourself. You can say C is the square root of you have to be careful. P21 minus P11, comma. This is now a row vector. P22 minus P12 multiplied by the same P21 minus P11, P22 minus P12, and the square root over it. And now you see that this is the same, because you're taking here the difference of these 2 terms. You multiply these 2 terms, so you get the squared operation. Is this clear? Well, this is actually great. We have now a method to compute some distance measure using vectors, and we don't care about the dimension at all. Let's nail that down. I take this one now. So we call this the L2 norm. Where our distance C is given by the difference between these 2 points, P2 minus P1. And this is typically the notation that we use to denote this L2 norm. So we have here this 2. And this is nothing else than the square root of P2 minus P1 transpose times P2 minus P1. And P is a vector and C is a scalar. P2, P1 are both vectors of whatever dimension, T times 1. If you can't read the times 1, forget it. We can also drop this times 1. If it's just a vector of dimension T, it means column vector. Now, in machine learning, sometimes we are not really interested in the Euclidean distance when we need to take the square root. So we don't need to know C in meters, centimeters, whatever. We just want to compare the C of one experiment with the C of a different experiment, and we want to know which of the two are smaller, larger, whatever. So if we look at relative distances, then we define the L2 squared norm. And this is now C prime because it's a different thing. And I'm again using the same notation with a subtle difference. I have here a second square, a second 2. So I take the squared to the power of 2, and then the square root is dropped. So the L2 squared norm is simply given by P2 minus P1 transpose times P2 minus P1. This is all very nice, but the L2 norm or the L2 squared norm, they have one particular issue. What is the major issue with this distance measure? Any idea? What is the nice thing about this measure? Think of gradient descent. Think of this optimization algorithm that we discussed. We talked about an objective, which we would like to minimize. What did we do there? We looked at the gradient. So we had to differentiate our equation, our objective, with respect to our parameters that we want to change, the model parameters. Now, what is the nice thing about this L2 norm? It's differentiable. That's a nice thing. What is the bad thing about it? Yes and no. Well, if you differentiate, you know what will happen if you increase your model parameters or if you decrease it. So that's not the issue. The issue is something else. The issue is the quadratic element here. If you compute the distance over your space. Now this is C here, the distance. And this is your space of potential points. And you compute the difference between P2 and any other point in your space. So here's P2 minus P2 is exactly here. So it's 0, which is nice. But if you have points that are very far away, Let's say this is some point 10 elements away, P10, and another one, P100, super far away. Now, what is the bad thing about the L2 norm? Exactly, you don't treat them equally well. For you, this P100 would have a way stronger impact because the distance that you compute depends quadratically on your distance measure depends quadratically on the difference between the points. So, which means it's a quadratic function and if this is an outlier in your data set, then your measure tries to first minimize the distance or error of this outlier. And even if all the other points are super nicely represented in your model, a single point can destroy the performance of your system. So the L2 norm is sensitive to points that are very far away, sensitive to outliers. We call that in machine learning. The benefit is we can differentiate it, which is nice for computing derivatives, for deriving update rules. Very nice. So what is the alternative to the L2 norm? What else do you know? Any other idea? Well, wouldn't there be a simpler measurement? Something called the L1 norm? What's the L1 norm? Well, I can compute again the same points. 1, 1 plus P22 minus P12, but with something in addition. I take the absolute values here, such that my measure is not sensitive to the direction. So this is the L1 norm, taking the absolute values. The L1 norm is linear. Lila is hard to read probably, but you get the point. The L1 norm is linear, so it doesn't matter if your outlier is super far away. It will have the same impact on your model updates, even for a point that is close by. The drawback is it's not differentiable in this point. Here you can't differentiate the model. Now there are two workarounds. I need some more space for that. Won't fit here. Yes. You're right. I don't need the square root here. Sorry, forgive me. Because we take the absolute value, the sum of absolutes. Good point. Hmm? Now, let's use this one. So there are two alternatives that I would like to present here. We have again, see the distance, we have our space here, and ideally, we would like to have a function that is linear and quadratic around 0. So that would be our dream ideal function. And what gets very close to that, this is the ideal loss or ideal distance measure. What gets very close to that, so it's a bit hard to draw for me here. This is the log cosine loss. So it's the log of the cosine of your distance d, p2 minus p1, log cosine loss. Then there's another one. This is A. There's another one that is commonly used that is called pseudo Huber loss. Why are these losses important? Well, you will face challenges in optimizing your models in the future. And one thing we can try different strategies is to change the loss function. And commonly quadratic loss functions are used, yes, but the log cosine loss might perform way better, or the pseudo-Huber loss. And here this loss function LP is given by, let me look at it. I don't know it by heart. Yeah. It has some parameter denoted by sigma here, which you can change. So it's sigma squared times the square root of 1 plus your distance measure, d, divided by your sigma squared value, minus 1. You don't need to know that by heart. The only thing I want you to know is there exist alternatives to the L1 norm, to the L2 norm. And you might see the L2 squared norm. That are the takeaway messages from the norms. I moved it up a bit. All right. And now a small example for the remaining 20, 30 minutes. Yeah, let's start with that one. Cosine hyperbolicus, good point. Let me first clean the blackboard, then I will check that, change that. Log cosine hyperbolicus, yeah, we call it log cosine loss. Let me check that first. The cosine of 0 is 1. The log of 1 is 0. So let's quickly check that before we do something wrong here. I have it anyways in the script. Let's have a look. That's why we have a script. Could be that I did not edit last year. This script is still work in progress. Good point. So the log cosine loss is not using the cosinus hyperbolicus. Have a look here. Define the pseudo-Huber loss. So here you see the pseudo-Huber loss. And if you compare it to what I wrote down, it's exactly the same equation. The only thing is that the distance is squared. And there might be different pseudo-Huber loss variants. Good point. All right, good that we clarified that. Now back to my example. So we want to make use now of all this new knowledge. For some of you, that might not be so new. For some, it might be new. But let's use that. Okay. We have an example where we flip a coin. We have a fair coin, or actually we don't know if it's a fair coin. So we observe if the coin lands on heads or tails, yeah? And we flip the coin many, many times. And here are some magic numbers. First experiment, 30 times tails, 16 times head. Second experiment, 60, 34. 90, 51. And then we call this X, we call this Y. And our goal is now to model that. Well, obviously, you could first try to sketch it. Say Y, X, and we have for X 3 sections, 30, 60, 90. You already see there is some trend here in the data. Then we have also here 3 sections, 15, 30, and 45. And now can add our observations. So for the first experiment, we had 30 and 16. So 16 might be somewhere here. Second experiment, we have 60 and 34, somewhere here. And the last experiment, here we had 90 tails and 51 heads, which is a bit more than the other one. Let's say it's here. Now you can say, okay, let's try to model that. We will model that with a linear model. Y is equal to kx plus d. You all know that, this model from high school. Now, if I would give you only 2 points, how would you solve it? You have done that, I'm pretty sure, all of you. You would define 2 equations. You would say y1 is given by k times x1 plus d, and y2 is given by k times x2 plus d. Then you would solve it for k here, for instance. K is equal to something, plug it into the second equation, try to solve it. You would compute your offset, linear term, and so on. Now, this is how we did it in the past. Now I will show you a solution that would work for an infinite, a very large number, not infinite, number of elements. And for that, we will define vectors and a matrix. Now, y is my target. Y is given by a column vector according to our notation, 16, 34, and 51. Here my question, can you read that? Otherwise, I will tell you, yeah? So this is my target, y, and I would like to solve that target or compute that values from some model matrix A times X. What is the dimension of A? No, I made a mistake. Sorry, that won't work. 8 times, and we need some model vector. We need here our 2 values, k and d, because these are the 2 parameters that we want to compute from our equation system. So k and d are our model parameters. We would like to compute them. They have the dimension 2 times 1. My target values have the dimension 3 times 1. If I want to match that, what's the dimension of A? A is now something that I will create. Three times 2, exactly. Three times 2, perfect. Now, I will simply continue here, but I will remove our sketch. We don't need it anymore. Now, how would you define this model matrix A? Just to remember, y1 is given by k times x1 plus d. y2 is given by k times x2 plus d. Now we have a 3 times 2 matrix. And we multiply it with k and d at 2 times 1. What do I need to put here? First element, or first two elements. If you look at this equation, y1, y2, y3. So y1 is given by this element times this one plus this element times this one. What do I need to put here? Almost. X1 is correct and the 1. X2 and 1. X3 and 1. And you could continue that for a d-dimensional vector. If you would have not only 3 observations, but 300, then you would have here 300 times 1 vector. You would have a 300 times 2 vector, but your model parameters stay the same. So that scales. So it's a very powerful definition of your linear equation system using matrix vector calculus. Any question to that? Then let's solve that equation system here. Oh, we still have a blackboard. That's nice. How do I compute x and d now? What can I do? I know my system. So my model is given by y. The vector is given by a times k and d. And typically, we say, okay, this is a times some model vector w. W are model parameters that we would like to learn from our data samples. W is unknown. How do I solve that? Let's do it step by step. I will multiply this equation with something. Who has an idea? Let's multiply it with A transpose. What do I need to write down now in the next equation? Next line. You multiply your equation system, so both sides here, from the left side with A transpose. Now you could check, is that possible at all? If you say A is of the dimension T times 2, W is of the dimension 2 times 1, then A transpose is of the dimension 2 times D. Y is of the dimension D times 1. So this works out. Here I forgot something. That's the reason why it's not working out. What is missing? I missed an A. You see? And by checking now the dimensions, we found out, well, I made a mistake. And immediately we find out, okay, now this is the product of B times 2. So we have A transpose times A, which is in the end of the dimension 2 times 2. What kind of matrix is that? No. No. So an identity matrix would have a special shape. You have ones as diagonal elements and all other elements are 0. So what kind of matrix is A transpose times A? So the thing is, the number of rows and the number of columns are equal. So it's a squared matrix. What is the nice thing about squared matrices? No? What is the nice thing about a squared matrix? They are invertible. So look at my equation here. We have A transpose times A times W. Now, if I multiply that with the inverse of A transpose times A, I get something that is very interesting. I get A transpose times A, the inverse of it, times A transpose times W is equal to A transpose times A, the inverse of it, times A transpose times A times W. Exactly. And here's your identity matrix. And why? Because you multiply the inverse of a matrix, of a squared matrix with the matrix itself, then this resides in the identity matrix. So we denote that by I, and I can drop that I don't need that. I can say now W, the vector, is equal to A transpose times A, the inverse of it times A transpose times Y. And this solution is valid for any d-dimensional vectors x and y. So now using matrix vector calculus, you are able to solve a linear equation system for d-dimensional systems, which is very powerful. One last thing. These terms here have a special name. Who knows how is that called? You get a bonus point for that one. Nope. But it has a special name. So we call this the pseudo-inverse. And you will see that frequently in our course, this term. And we will make this equation nonlinear. We make it complex using feature transformations, but it will be all based on the simple linear equation system that we derived now together here in this lecture room. All right, that was my example. Hope you enjoyed it. If you have any questions, I'm still around.